So in this video we proved the last theorem of this chapter, which in practice is really one of the most useful. It's due to Banach and Alaoglu in its most general form, and what it says is that the closed unit ball of the dual space X star endowed with the weak star topology is a compact topological space. Now, the way we prove this is really by applying an important theorem from general topology, which is due to Tikhonov, and tells you that products of compact spaces, doesn't matter if the product is finite, countable, uncountable, will remain compact. So I'm going to show you how we apply this. So we define a map phi from this topological space Bx star handled with the weak star topology into the space of functions from X to R by sending a functional to the set of real numbers, the product of all those real numbers that you obtain by applying X star to X, running that over all X in your Banach space. Now, if you define the range of this map and call that A, it certainly would be included in the product of the intervals minus norm of X running through the Banach space. So it's a massively uncountable product, but it's a product of closed intervals of R. Right, you're in that because X star has norm less than 1 because you're in B of X star, right? So X star applied to X in absolute value cannot be greater than norm of X. But then what the Tikhonov theorem is telling us is that this product, as gigantic as it may be, because it's a product of compact space, returns a compact space. So this product here, as a topological space, has to be compact. Okay, but now how do we get our theorem from the compactness of that set? So we will show two things. So one, that A is closed. And then a closed set inside a compact one has to be compact. So, okay, so A will be compact. And two, we will show that A is homeomorphic, so and the homomorphism is given by phi. So is a homeomorphism from, well, between Bx star and with the weak topology, of course. Homeomorphism is continuous between the unit ball with the weak topology and A. So if you're homeomorphic to a compact topological space, then you have to be a topological space yourself. Right, so these are the two steps. Prove that A is closed and prove that phi is continuous for the appropriate topologies. Right, so let's start with 1. How do we prove that A, which is the range of phi, is closed? Well, we take a element lambda, which is really a set lambda x of reals indexed by x in the Banach space in the closure. And we're going to need to show that lambda is actually in A. So what does that mean to show that lambda is in A? It means that the map that sends x to lambda x is continuous, is linear and continuous. So we're going to show that this is linear, and we're going to show that lambda x is smaller than x for x, right? And then this would give that lambda really is the image by phi of the functional x goes to lambda x, which will be a functional, an element of B of X star, because you have a continuous linear map of norm smaller than 1. Now, to do that, I need to understand what the neighborhoods of lambda look like. So if I give myself a epsilon and some x1 till xn in my Banach space, some n in n obviously, then I'm going to define, I should say for this, define a neighborhood that I'm going to call u epsilon x1 till xn. It's very similar to a weak star neighborhood, but it's not quite the same thing, to be the set of mu x, x in R to the x, such that mu xj minus lambda xj is smaller than epsilon for all j equal 1 to n. Now that is a open set in R to the x, right? By definition of the product topology, I'm really taking now here a finite product of open sets in R. Now, okay, this is open in R to the x, therefore it has to intersect, and it's an open set that certainly contains lambda, because lambda xj minus lambda xj would be 0. So this has to intersect A, because lambda is in the closure of A. And that's fundamentally what I'm going to use for appropriate choices of such neighborhood. I'm going to deduce 1a and 1b, so the fact that x goes to lambda x is linear and lambda x in norm is controlled by the norm of x. What do I mean by lambda x in norm? It's an absolute value because I'm in R. Okay, so how do we do this? Let's do 1a first. So for 1a, I'm going to give myself an x0 and a y0 in x. I'm going to look at x0 plus y0. I'm going to look at an alpha in R star. I need to look at alpha times x0 to prove linearity. And then I'm going to give myself an epsilon, arbitrary epsilon of room. And now, okay, so the first thing is to say I have u of minimum epsilon and epsilon divided by absolute value of alpha at x0 and alpha x0. This has to intersect A. Okay, so what does that mean that it intersects A? Well, that means there is an element of the range of phi that is also in that neighborhood. So let's take that element. Let's take x star in B of x star such that x star tested on x0 is close enough to lambda x0, and the close enough would be smaller than the minimum of epsilon over alpha. I want this one with epsilon over alpha. You'll see why in a second. And then I want x star tested on alpha x0 to be close enough to L of alpha x0, close enough up to that epsilon, right? So I can do that because this is phi of x star is the element in my neighborhood U, and being in the neighborhood U exactly means that. So what does that give me? That gives me that alpha times lambda x0 minus x star alpha x0, using the bilinearity of the duality product, is smaller than alpha. Right. And in the meantime, x star alpha x0 minus lambda alpha x0 is also smaller than alpha. So we get that for every epsilon, alpha lambda x0 minus lambda alpha x0 is smaller than 2 epsilon. And therefore, well, it's for every epsilon. So lambda alpha x0 has to be alpha of lambda x0 for all alpha in R star. So that gives us part of the linearity, at least for alpha non-zero. But for alpha equal 0, we would get that x star comma 0. Just take the neighborhood U epsilon x0. This has to intersect A, and then we would get that x star tested on 0, which is 0 minus lambda 0, testing at 0, has to be smaller than epsilon, and that implies for every epsilon. So this implies that lambda naught has to be 0. So in particular, lambda of 0 times x naught has to be 0 times lambda of x naught. So we have lambda alpha x naught is equal to alpha lambda x naught for all alpha. Well, it's not quite alpha because our alpha was not 0, but for all beta in R. Okay, so that's part of the linearity, but now I have to look at lambda x naught plus y naught. Now, this works almost exactly in the same way. So what you do is that you say that u epsilon x naught, y naught, and x naught plus y naught, that's another open set in R to the x that contains lambda, has to intersect A, because lambda is in the closure of A, and so you can pick an x star in B of x star that's going to be such that x star x naught is close to lambda x naught, x star y naught is close to lambda y naught, and x star x naught plus y naught is close to lambda x naught plus y naught. Okay, and now using triangle inequality, you get that lambda x naught plus y naught minus lambda x naught minus lambda y naught is smaller than 3 epsilon for all epsilon. So lambda x naught plus y naught has to be equal to lambda x naught plus lambda y naught. This proves 1a, i.e. x goes to lambda x is linear. Now for b, same sort of idea. You just say there exists an x star in the unit ball of x star such that x star x is close to lambda x. Alright, and now that gives you that lambda x is smaller than norm of x, because x star is in B of x star, plus epsilon for all epsilon, and therefore lambda x is smaller or equal to norm of x. And so we have proven that A is equal to a complement, because we've to a closure, because we've taken a lambda in a closure and we've shown that it's necessarily in A, and that tells us that A is compact, right? Because it's included in a compact set, and we've seen, well, it's included in this infinite product of compact sets, and that set has to be a compact space by Tikhonov theorem. Right, so last thing we have to prove is that A is homeomorphic to B of x star, or boy of x star is homeomorphic to A. Okay, so how do we do that? Well, first of all, let's notice that phi is a bijection, because if I have x star and y star in B of x star, and phi of x star is phi of y star, well, what does that mean? It means that x star minus y star x is 0 for all x in x, and that's exactly saying that as linear functional they are equal. Right, so phi is a bijection, right, because it's injective, and of course it's surjective onto its image. What is B x star? It is phi minus 1 of A, because A is the image of B of x star by phi. Right, so I want to show that my B of x star is compact. So what I need to show is that phi minus 1 is continuous from A with this product topology to B of x star with the weak star topology. And well, phi minus 1 being continuous really means that phi minus 1 sends open set to open set, and phi minus 1 is phi. So we need to show that for every, let's call that O included in B of x star that is open, phi of O as an element of this infinite product is open. And of course, you only have to do that for every, maybe, oh, I should write my O like this. You only have to do that for neighborhoods because they generate the topology. So if you're continuous, if you send any set that generates the topology to an open set, then your inverse, sorry, is a continuous map. So what we have to show really is that for every epsilon and for every n and for every x naught in B of x star and for every x1 till xn in x, when I look at a neighborhood in the weak star topology V epsilon x naught star x1 till xn, and I want it to be in the induced topology on the unit ball, so intersected with the unit ball, I want to show that the image of that by phi is open in A. Okay, so what do I need to do? I pick a element in that image. So let's lambda in phi of V epsilon x0 x1 till xn intersected bx star. So this lambda is going to be a phi of some, let's call that y0 star, for some y0 star in B of x star and intersected V epsilon x0 star x1 till xn. Right, and what I need to do is I need to find a neighborhood of lambda in A that is included in phi of this. So what is it going to be? So notice, what can I say about my y0 star given that it lies in here? Well, I can say that y0 star minus x0 star tested on any of the xj, this has to be smaller than epsilon. And so if it has to be smaller than epsilon, I could pick a delta such that this is smaller or equal than 1 minus delta epsilon for j equal n. And I can pick a delta in 0, 1 that does that. Now, given that delta, I'm going to define a neighborhood of lambda in A in the following way. I'm going to consider u epsilon x1 till xn to be the set of all those mu x, x in x that are close enough to lambda x. So mu xj minus lambda xj is smaller than epsilon for all j equal 1 to n. Right, now this, if I intersect that with A, is open in A, and I want to show that this entire open neighborhood of lambda actually lies in phi of this open set in Bx star. So okay, so let's do that. So take a element mu in u epsilon x1 till xn, and I have to show that it's in the right spot. So, this is in that intersected A, so I have a certain element y star in Bx star such that mu is phi of y star. And now what I need to show is that y star belongs to V epsilon x0 star x1 till xn. And if I can do that, then I'm done. I mean, phi of A intersected this neighborhood, and that is true for a generic element in this open set. Therefore, I found a open neighborhood of any element in the image of an open set in Bx star by phi. So, okay, so let's take a j between 1 and n, and I have to show that y star is close enough to x naught star. And what can I say about y star minus x naught star tested on xj? It is what? It is phi. So it is really mu of xj minus lambda of xj plus lambda of xj minus x naught star xj. Right? Of course, y star xj is mu xj, and I introduced lambda xj because I know that mu xj is close to lambda xj. So now you use triangle inequality. Mu xj is close to lambda xj. It's close up to epsilon delta over 2. Ah, yes. I didn't choose my neighborhood correctly. I should have multiplied that by delta over 2 here, because if I do that, if I make the neighborhood that small, then what I get is that this is smaller than epsilon delta over 2 plus lambda xj minus x0 star xj. And now this is smaller than epsilon delta over 2 plus 1 minus delta times epsilon. And that is 1 minus delta over 2 epsilon, which is strictly smaller than epsilon. And that concludes the proof, because that means that this neighborhood of lambda is included in the image of this neighborhood in B of x star. So my phi maps open set to open set. That is to say, my phi minus 1 is continuous. And because B of x star with the weak star topology is the image under this continuous map phi minus 1 of A, which is compact by the first step of the proof, then B of x star and with the weak star topology has to be compact.